This is part 2 of the video notes for Objective 2E, Exponential and Logarithmic Models. In this part of the video notes, we're going to talk about a specific application of the exponential functions, the financial model. So at the top of your notes, you have the three formulas for simple interest, compound interest, and continuously compounded interest. It's important to note that simple interest is not an exponential function because it represents a constant interest amount added each year. Compound interest, on the other hand, whether it's continuous, annually, biannually, quarterly, daily, etc., is going to be an exponential function, and the amount of interest earned is going to increase each year as the account balance increases each year. So example 8 is asking you to compare the interest rates for 2.02% continuous, for 2.04% annually, and for 2.03% quarterly. All of these interest rates are similar, but you'll notice that the highest interest rate has the least amount of compound frequency, and we're going to type each of these into our calculator to determine the effective interest rate. So using just the inner part of our formula, we're going to say that this is e to the RT, or e to the 0.0202. The next one, using the inner part of the compound interest formula, we get 1 plus 0.02 over 1, 0. We get 1 plus 0.0204 over 1 to the first power, representing an annual compound. And then for our quarterly, we have 1 plus 0.0203 divided by 4 for quarterly to the fourth power. Type each of these expressions into your calculator to estimate the effective interest rates. So for the first one, we have 1.0204. So this 2.02% continuous becomes 2.04% effective. Then we type this one into our calculator, and as you can see, to the first power and divide by 1 isn't going to do a whole lot. This is also 1.0204. So let's see how the quarterly interest rate shakes out when we type it into our calculator. And so this interest rate becomes 1.0246. And because this requires us to round up, we find that the middle range, the 2.03% quarterly, is a better effective interest rate than either the 2.04% annually or the 2.02% continuously. Example 9, we're talking about a bank deposit called a certificate of deposit, which is a higher interest rate savings with a fixed time before you can access the funds. And the bank is offering you 1.1% compounded annually if you have a minimum balance of $1,000. So let's apply these to our compound interest formula. This simplifies, so I'm going to go ahead and replace this with 1 plus 0.011. And then I have multiple questions, so I want to plug in different values for the exponent time. And so the first one, it asks for 1 year, which will be $1,011. And then the next one asks for 5 years, so I need to plug in 5 to my exponent, t, and I get the result of $1,000 $56.22. If I raise it to the 10th power, I get $1,115.61. And then the last question says for 25 years, and so if I do to the 25th power, I get $1,314.56. Example 9. In an episode of Futurama, it is revealed that Fry still has an account with 93 cents and an interest rate of 2 1/4 for 1,000 years. Now, keep in mind, this is an unrealistic interest rate, but it does make for a great episode of Futurama. If Fry's bank compounds continuously, how much money does he have right now? So we're going to be using the compound continuous function with an initial balance of 93 cents and a rate of 0.0225 for 1,000 years. And we find that Fry has $5,496,785,518.62. For the next section of this video notes, we want to take a look at some other applications of exponential functions. And so money is one application, and it's an important one, but there's also something called uninhibited growth, which is often the population growth model used for countries or for bacteria or pretty much anything that grows. So the compound continuous model is also used for uninhibited growth. And so our model used to be A equals PERT, and now it's going to be A equals A naught e to the KT. So just slight adjustments in the variables because we're no longer talking about a principal and an interest rate. We're talking about an initial value and a growth rate. Example 11 asks us to rewrite the population models for the US and for Mexico using continuous growth rather than exponential growth. So the US model would be 325 million e to the 0.007t, and the Mexico model would be 125 million e to the 0.013t. How does this change our answers? So the first question was, what's the population of the US in 1 decade? And we would plug in 10 for the value of t, and we would find that the population would be 348.56 million people. How does that compare to the original answer? Is there a significant difference in the population? The second question was, when does the population of Mexico exceed the population of the US? And we'll need our calculator and we'll need to set up our tables. And if you remember, the last answer was 161 years. And so we'll type in the first model, 325 e to the 0.007 x, and we'll type in the second model, 125 e to the 0.013 x, and we'll create a table with the same table settings that started at 160 and counted by ones. So looking at our table, you can see that it's actually a little bit earlier. we'll have to change our table settings. We can see that Mexico does exceed the US population at 161 years, but we can also see that it exceeded it back at 160 years. So I'm going to go back 10 years, and I'm going to start my table at 150. And if I look at the detail here, I can scroll down. I can see at 156, the US population is still larger than the Mexico population. And it doesn't change until 160 years. So switching to a continuous model means that the Mexican population exceeds the US population 1 year sooner than before. Example 12. A virus begins with a single specimen, patient 0, and grows continuously at a rate of 50% per day. Write an exponential model to determine the number of infected people after t days. So, number of infected people. The initial is just one person. It's a continuous function, and the rate is 0.5. Here's my model. How many people are infected after just 1 week? And the answer is 33 people. How many people are infected after 1 month, which we'll assume is meant to be 30 days? In 1 month, 3,269,017 people will be infected. And the last question is, how many people would be infected after 1 year or 365 days? And we can see that the number is much too big to write down. I don't know if you can see that screen, but that's an e to the 79th power, which means it's 79 digits of people, which would exceed the world's population. Next example. A colony of ants begins with just 10 ants and after a month has expanded to 12 ants. Assuming the population is following continuous population growth, construct an exponential model. So we're going to start with a naught e to the kt, and we know that it began with 10 ants, and we know that after 1 month it had 12 ants. So we're going to solve for the rate of growth. First, divide by 10. Then use a natural log as the inverse of e. And we find that our growth rate is ln of 1.2, or approximately 18.2% growth. So the final model is A equals 10 ants, e to the ln 1.2 t. How many ants will there be in 1 year? Plug in 1. Plug in 12 for time, since in this case time represents months instead of years, and we get that there would be approximately 89 ants after 1 year. Now, even though this growth rate is 0.182, it still represents growth. Previously, in an exponential function, if you had a factor of 0.182, you couldn't necessarily guarantee growth. And that's because in an exponential model using e, if k is greater than 0, you have growth. And if k is less than 0, you have decay. As opposed to our other model, in which case if b is greater than 1, you have growth. And if b is between 0 and 1, you have decay. And the big difference is that this represents a factor and this represents a rate. Let's take a look at a few decay examples to see the difference between growth and decay. Imagine the car that depreciates 18%, is from the previous example, and instead it decayed continuously. How would we write an exponential model? We'd have A equals, and then the initial value of that car was 25,000, and then we'd write e to the what t. When we previously wrote this equation, the what was 1 minus 0.18 or 0.82. But now that we're using a continuous model, the what is negative 0.18, because in a continuous model, negative rate indicates decay. How do the two models compare after 10 years? So our first model versus our second model if we plug in 10. And so in our exponential decay model, we see that the value of the car is 4132.47 or $4,000. And in our other model, we see that the car value would be $3,436. And so we don't get the same value of the car with exponential decay, with continuous decay, that we do with a standard exponential decay. Finally, there's a subset of exponential problems called half-life problems. And you should be familiar with half-life problems because they come up time and time again in both mathematics and science. So a half-life problem requires you to solve for the missing rate and then use that rate to solve extra problems. So our question is, how long will it take for a 40-gram sample of I-131 with a half-life of 8.04 days to decay to 1/100th of its original size? So step 1 is to find the decay rate, and we use the half-life information to do this. 1/2 equals e to the k 8.040 days. Use a natural log and divide by 8.040. The decay rate is negative 0.0862 or 8.62%. When we type this into our formula, we're going to use the exact value, which is ln of 1/2 divided by 8.040. Let's back it up. Once you have the rate of decay, you move on to step 2, which is to create a model and actually solve the problem. So in this example, we have 40 grams initially, a decay rate of ln 1/2 over 8.040 to the t power. And the question is, when will it be 1/100th of its original size? Well, the original size is 40, and 1/100th of 40 is 40 divided by 100, or 0.4. Watch what happens when we divide both sides by 40. 0.4 divided by 40 is 1/100th. When you're solving an exponential problem like this, the amount you start with often doesn't change the problem because it's all based on what percent you grow or decay by. If I'm going to get to 1/100th of my original size, it doesn't matter what my original size is, I'm trying to reach 1/100th no matter what. From here, we need a natural log. And And we need to divide by this coefficient, which is the same as multiplying by its reciprocal. So on the right, I can multiply by this, and that cancels, And on the left, I multiply by the same thing, and I type all of this into my calculator to find t. So 8.040 divided by ln of 1/2 times ln of 0.01. And we find that it would take this particular isotope 53.4 days to reach 1/100th of its original size. The next example is Newton's law of cooling, and this is a unique model that follows exponential decay. And it basically says if you have an object heated to a specific temperature, it will cool exponentially until it reaches the ambient temperature, the temperature of whatever's around it, whether it's air or some compact substance. So the formula is U of T. T is the ambient temperature, so the temperature of the substance around it. U naught is the initial temperature the object is at. And then K is the rate, or the exponential rate of decay. So the temperature of the object is equal to the ambient temperature plus the difference between the starting temperature and the ambient temperature times some exponential rate over time. Our example is an object heated to 100 degrees Celsius that is allowed to cool in a room whose air temperature is 30 degrees Celsius. Here's my initial equation, and I'd like to simplify this. So it's in a room that's 30 degrees, and the difference between the room's temperature and the object's temperature is 70 degrees. Now let's get to the first question we need to solve. If the temperature of the object has reached 80 degrees Celsius after 5 minutes, when will the temperature reach 50 degrees Celsius? Step 1 is to find the rate of decay. So I know 80 degrees after 5 minutes, and I can solve this by first subtracting 30 to both sides, then dividing by 70, then using a logarithm, and dividing by 5. So our approximate answer, and I just like to see the rate for myself, our approximate answer is that the decay rate is negative 0.067, or about 6.7% loss. I'm going to use the exact rate when I plug it back into my equation to finish solving the problem. So my original is here, and I'm going to erase everything after this point. Now I want to know how long or when the temperature will reach 50 degrees. But I now know the rate is ln of 5/7 over 5. Let's solve for t again. Subtract 30 to both sides of the equation. Divide by 70. ln both sides. And multiply by the reciprocal. And we find it takes about 18.6 minutes for the object to reach 50 degrees. Same setup, different question. So I'm going to back it up. And now answer how long it will take the object to reach 35 degrees. Using the exact same steps. So 5 equals 70 e to the ln 5/7 over 5. Divide by 70. And I'm using my calculator and I'm fractioning my answer because it is a decimal and it is not exact. I'm going to ln both sides. And I'm going to multiply by the reciprocal. And I find that it'll take 39.2 minutes for the object to reach 35 degrees Celsius. So there's an example of Newton's law of cooling and how you should use the formula to solve. Our last unique example or unique application is a logistic function. So most populations can't experience uninhibited growth because there are limits to food and space and other factors that influence how a population grows. A logistic function approaches that realistic limit or maximum that a population can reach. So the logistic model, and we'll just jump straight into the fruit fly population. The logistic model starts with the carrying capacity. So the number in the numerator represents your maximum population. Underneath, you have a couple of constants that are going to be unique to each problem. So we have 1 plus a, which is some constant ratio or rate, 56.5. E to the, again, we have a constant decay rate here, and t. And so normally this would be the initial value, but because this function has a lot more going on to it, we can't just assume that the initial value is 56.5. We can, however, assume that the carrying capacity is 230. So question A, what is the carrying capacity? 230 fruit flies are the maximum number of fruit flies that can be grown in this half-pint milk bottle. What's the initial population? The way to find that is to plug in 0. And we want to use our calculator to do this. E to the 0 is 1, and so we're basically going to type 230 divided by 57.5. And we find, oh, it's an exact answer. There were exactly 4 fruit flies in this half-pint bottle when the experiment began. What will the population be after 5 days? So we're going to take this equation and we're going to plug in 5. Use your calculator. Make sure you put a pair of parentheses around your denominator so that it all gets grouped together by your calculator system. And so I've got a population of about 23 fruit flies after 5 days. Then the question is, how long does it take the population to reach 180 flies? So I know that I'll get to 230 flies eventually. And 180 is less than 230, so this does not exceed our maximum. And I am going to solve this crazy, rational, exponential logistic function for the variable t. And I'm going to need a lot more space. So let's erase all of the original. All right. Step 1, I don't like having my variable in the denominator. I'm going to reciprocate both sides of this equation. So I'm going to reciprocate to 1 plus 56.5 e to the negative 0.37t over 230 equals 1 over 180. Then I want to try and get the e by itself. So I'm going to multiply both sides by 230. These 230s will go away, and this 230 will become my numerator. The next step is to subtract 1 from both sides. This 1 will go away. And allow your calculator to do the subtraction for you if you need to. This should be 50 over 180, which your calculator will simplify to be 5 over 18. Now we're going to divide both sides by 56.5. Remember, division is also multiplying by a reciprocal. I'm going to write down my rounded answers for my calculator here, but I'm also going to save the exact answer in the calculator so that I'm not using rounded values to calculate. So here we have e to the negative 0.37t equals 0.0049. Notice in my calculator there are more decimals than just the 4, and so when I go to do the ln, turn this into a log, even though I'm writing 0049, this is not what I'm typing in my calculator. In my calculator, I'm typing the ln of second answer, and then I know the next step is to divide both sides by negative 0.037. 0.37, 0.37, 0.37. And so right in my calculator where I have ln answer, I'm going to divide by negative 0.37. And so we get a result that t is equal to about 14 days. 14 flies. But let's calculate this inflection point. And it gives us a chance to practice these solving skills. So I'm going to say 115 flies is equal to 230 over 1 plus 56.5 e to the negative 0.37t. Reciprocate. And you could do this by cross multiplying. You'll get the same result. Subtract 1. And then I'm going to use my calculator for this one instead of my mind. Could have predicted that. So 230 over 115 minus 1. This is just 2. Because this is half of that. Oh, gosh. Divide by 56.5. E to the negative 0.37t equals 1 divided by 56.5. And wow, that's a very small number. So again, I'm going to leave it like this. 1 over 56.5. And I'm going to ln both sides. So I get the natural log of 1 over 56.5 equals negative 0.37t. Divide by negative 0.37 and type this into your calculator. And we find that it takes only 10.9 days or 11 days to reach half of its carrying capacity. So let's take a closer look at this function. Now that we have some values, we can make a table. We know after 0 days, there are 4 flies. And we know that it takes 10 days to reach 115 flies, half the carrying capacity. We also know it takes 14 days to reach 180 flies. How do you get a function that grows like this? So I want to make a graph using my calculator of this logistic functions. In the y equals, type the entire function and be sure to put parentheses around your denominator. Then I like to do zoom standard, which doesn't work for this function, but it does reset my calculator settings. And so you can see a little bit of the exponential growth portion. But a logistic function is interesting because it has exponential growth up until an influential point, and it starts to slow down. So let's change our window to make sense in this problem. For example, there are no negative days. And my X-max has to be more than 14 because it took 14 days to reach 180, and I know that my maximum is going to be 230. So let's double it-ish and do 30 days. Then our Y minimum shouldn't be negative because there aren't negative fruit flies, and our Y maximum should be 230, but I'm going to go ahead and make it 250 so that I can see the whole picture. Now let's graph. This is a logistic function. It experiences exponential growth until the halfway mark, half its carrying capacity, and then it becomes logarithmic growth, where it's slowing down with an exponential rate. This concludes part 2 of the video notes for exponential and logarithmic models. In part 3, we're going to take a look at regression, scatter plots, and using your calculator to fit a function to imperfect points.